is equal to ft. Well, that's an interesting relation. You're not always going to get this. We have a constant force here, right? Well, understand that since F is dP dt, P can be seen as the integral of F dt, right? All I'm doing is reversing the differentiation. If for a constant force, this is indeed what we get. And we're going to get some constant, but that's due to initial conditions. And I said for this example that my initial conditions were zeros. Now, it's also quite important to say that I can say a change in momentum can be seen as a force times a change in time. It's a bit weird, but what we can get from this is delta P over delta T is equal to F. Now this is actually not true because we have a derivative definition for momentum. I need something else instead of momentum to have here to make this true. And so the new quantity that I invoke is called impulse, or I. Impulse is kind of like the non-limit definition. It's an approximated version of momentum. And so when you take the limit as delta t approaches 0, you get P. That's called like the impulse momentum formula. What we get, though, is roughly the same thing. You're not going to be using impulse that often, but impulse and momentum have a nice relation to each other that we can take advantage of. Now, that kind of does, that finishes the first example. Now, let's say instead I have, instead of acceleration going in the general x direction, I have acceleration pulling a mass downwards, okay? Now, this g vector is essentially negative g j hat, where negative j hat is the direction. Well, I say this because I define my y-axis to be pointing up. Another thing that you want to do when doing problems, establish your axes. If your x-axis is pointing horizontally and your y-axis is vertical, you have to stick with that. Now, we can essentially do the same stuff that we did in the last problem, but I'm not going to spend too much time on that. I'm just going to quickly define a new vector called w. This is known as the weight vector. Some texts have this as a lowercase w. I like to use an uppercase w, which is just mg. Everyone has weight. Just there's a difference that I want to highlight between mass and weight. Weight is highly dependent on the gravity of the planet you're standing on, where m, mass, is just an inherent quantity that everyone has. If you're standing on Jupiter, you'll be heavier than if you stand on the moon. Easy peasy. Because the gravity is stronger and therefore has a larger magnitude. Now, let's cover another example. Let's say I'm standing on the Earth, right? And I have some mass, m. One of the most important things you're doing when you solve force problems is in setting up the free body diagram, right? The free body diagram is when you set up the center of mass, right? And you talk about the forces acting on it. So we know that weight is a force acting on this. It's going to pull it down. Well, if that were the only force, then motion will be in this direction. And you just constantly accelerate and accelerate and accelerate. Now that's called falling. You're not going to fall to the ground. So there's obviously something different happening here, right? There's some other force that's counteracting this weight. What could that be? Well, we call that the normal force, or N. The normal force is kind of just like the action of Newton's third law. Every object will push back on you to some extent, right? Now, this isn't like pushing on a fridge. You're not going to both go in different directions after all, because the Earth is rather large, and there's going to be no real displacement with extremely large objects. So, in all for all intents and purposes, this one is going to give us this equation. Or the magnitude N is equal to mg. Now, important thing here, I drew a vector equation here, and I drew a scalar equation here, right? So the vector equation is really just going to be one's pointing up, one's pointing down, right? So we have one vector is definitely equal to negative of another. But over here, I've equated the two without a negative sign. Why did I do that? Why did I have two vectors here and then express that they're in opposite directions, but not have a minus sign when expressing their magnitudes? Well, the answer would just be that the magnitudes are the same, the length of the vector. This equation is only concerned with lengths of vectors. So if you put a minus here, you're in big trouble. Don't do that. Just a general rule of thumb. You want to kind of keep track of these because you want to make sure that you know exactly what you're doing with these vectors. Like, for instance, in other problems, we'll have some vectors that are just going all over the place. We'll have some free body diagrams like this, maybe some other force here, and if they're all the same length, you don't want to have negative signs on certain ones because negative length is a bit of a hairy concept. Moving on to another example. The normal force is adjustable. It really depends on what load you put. It doesn't really depend on what mass is sitting there, but rather what load is put on it. I'm going to have a flat surface and some brick of mass m sitting here. But the surface has kind of a hole, and the mass is sitting over the hole. Attached to the bottom of this mass and through the hole, I have a string. And I'm pulling on this mass from above. I'm not hanging, I'm actually just standing on the ground. I'm pulling on this string, I'm exerting another force other than gravity. So its weight vector is going to look like this, but there's another force here called T. I call this the tension force. Tension forces are usually existent in strings. When I pull a string, I make it taut, and so the force kind of transfers along that line and pulls whatever it's connected to. Now, this mass isn't going to move anytime soon, so its normal force has to match W and T. This is, again, static equilibrium. If we're in static equilibrium, we always have to keep this into account. F net is equal to 0, right? In other words, N is going to be the negative of W plus T. If I write its magnitude equation, though, N is equal to W plus T, or mg plus T, particularly speaking. And so this is just to highlight that my normal force isn't just anti-weight. It's really just kind of a counteractive weight for whatever, or a counteractive force for whatever force I put on a surface. Normal force is going to be perpendicular, or normal to, the surface that it's lying on, right? There are three words for this concept. There's perpendicular, there's orthogonal, and there's normal. Just get used to those concepts existing. Now, next example, I'm going to talk about how we can split these forces up into its angular components, or its x and y components. So, let's say I have a mass here, and I have connected to this mass a string on its corner, and I'm pulling this string in this direction. It's some angle theta off the horizontal, and I'm pulling it like this. But let's say I'm not strong enough to completely lift it off the ground. So there's still going to be some weight that counteracts it. So just like if I pull down on an object, the normal force will increase to match it. If I pull up on an object, the normal force will decrease just to match that vertical component. There are such a thing, like a lot of times in Physics 1, people have the misconception that normal force is a static value and doesn't change depending on the load you put on it. But it does, and that's an important distinction to make. We're going to draw the free body diagram for this system, where I have the mass here, I have its weight, and I have its tension here. And it's going to have some normal force. It's not going to be as large because I'm lifting the burden off of it, but it's going to be large enough to counteract the weight. The thing is, now I'm invoking two directions, right? If I pull it, and I'm not going to lift it off the ground, it's going to end up moving in this direction. This is not a static equilibrium problem. However, it is in the y direction, right? And for the rest of this lecture, unless I say otherwise, we will assume that x is in this direction and y is in this direction. So down here is negative y. So it's not moving up or down, so we can say the net force in the y direction is entirely zero. All right? What we can do there for that. An important thing that we want to know then is what is the horizontal and vertical component for this tension vector here, offset by the horizontal at some angle theta? Well, we can split this up. If I have any vector offset by some angle, the vertical component will be a sine theta, and the horizontal component will be a cosine theta. Right? So I can rewrite this now as the weight vector coming down here, the normal force up here, t cosine theta, it's going to go in that direction, and t sine theta added to this normal force to completely counteract the weight. All right? So we have two equations that we can really talk about now. First of all, these two are equal to each other. I can set the magnitude of the weight vector, mg, equal to the magnitude of this guy, which is t sine theta plus n. Therefore, I can say that the magnitude of the normal force is just going to be mg minus t sine theta. Everything is balanced as it should be. Now I'm going to have some net force in the horizontal direction, which means that this object is going to accelerate, right? If I have a total net force that's non-zero, in the direction of that net force, the object will accelerate. So again, points to consider when solving a force problem. Make sure you draw the free body diagram. Make sure you can tell when the system is in static equilibrium or not, and treat the system differently depending on that, right? If it's in static equilibrium, the forces will sum together to become zero. If it's not, the forces will not sum together to become zero, and there is net motion, hence an acceleration. We can now say then that this force, or at least the magnitude thereof, is going to be equal to the mass times some acceleration, right? According to Newton's second law. A then is going to be t cosine theta over m. And we can go back to the kinematic equations and use that to talk about moving a certain distance or taking a certain time to get to that distance, etc., etc., etc. Now, are we good here? Can I erase this? Awesome. Next example. We're going to start to pick up the pace a little bit and get into a tougher example. I'm going to talk about the Atwood machine. The Atwood machine, it's very important. So important that it's given its own name. The Atwood machine is essentially a pulley with two masses hanging off the edge. Okay? A pulley, all it really does is it redirects force. I'm going to have two masses hanging off one end and the other end. Okay? Now, let's say that these two masses are equal. Or actually, let's not say these two masses are equal. Oh, no, yeah, if they are, what's going to happen? No motion at all, exactly. This mass isn't going to go down while this mass goes up, unless there's a tiny discrepancy in mass, in which case we were wrong in our premise. But generally speaking, what's holding these together? If I have a system of two masses, then I have to draw two free body diagrams. For every mass that I have, that I kind of want to look at separately, I'm going to want to have two different free body diagrams. All right, so I have a mass here, and let's take a look at mass 1, where this is going to be m1g. The force going down is going to be m1g. There's some force pulling it back up. Well, it's a force in a string, so I will call this tension T1. Okay? Over here then, for mass 2, I have m2g, and a force pulling it up, T2. These are exactly equal to each other, all right? First of all, a couple things. Now, essentially, even though T1 and T2 are pointing in the same direction, they're actually pointing in opposite directions, right? If I have T1 pointing up here and T2 pointing up here, and I took the pulley away and laid the string out flat, they would be pointing in opposite directions. Do you see what I mean? Yeah. All right. That being said, their magnitudes are still the same, so I will equate these two together. Now, there's no net force for either mass, so I equate these two forces together, which essentially means that these two are equal to each other. m1g is equal to m2g. I can cancel out a g, and I'm back with my initial presupposition. But I didn't assume that the masses were equal at first. I got the result that m1 is equal to m2 by assuming that there was no net motion. That's an interesting thing. We can kind of go backwards now with our force laws. Moving forward on this, let's get to the hard part that everyone dreads about the Atwood machine. Let's assume that the net force, that m1 is not equal to m2. All right? There is some acceleration. Okay? Let's assume for now that m1 is greater than m2. Okay? If m1 is greater than m2, then m1 is going to go down with some acceleration a. Right? Well, then what about m2? How is it going to move? So it's going to move up. At what acceleration? Right, the same acceleration that m1 is going down with. Now, on a pulley, if this one is going up and this one is going down, they're actually going in the same direction, because all the pulley does is redirect force. Now, let's get into some of the more hairy details. For m1, I'm going to have m1g pointing down, right? And I'm going to have some tension, T1, or I'll just call it T, pulling it up. And the net force will be A. Now, for this particular problem, I'm going to say on this side of the pulley, this direction is positive, which essentially means that this direction is positive. Right? Awesome. Now, for this side of the pulley, since T is pointing up, is this going to be positive or negative? Or in the positive or negative direction? Yep. What I mean to say is, since my weight is pulling down and my tension is pulling up, and this, I've already said, was the positive direction, T is pointing in the negative or positive? Negative direction. Okay. So in the end then, I can say M1G, or M1A, right? The net force on this object, since it's accelerating down in this direction, is going to be M1G minus T, right? Does that make sense? Because it's going down in this direction, this contributes to the quantity while this does not. Now we can talk about the second one. M2G and T, again, up here. All right? Now, on this side of the pulley, I said that A was pointing in the positive direction up. So this direction is positive or negative? Negative. So M2G is going to be minus. There's going to be a minus in front of it. So for the T, the tension for this part is going to point up. So m2a is going to be t minus m2g. See where I'm going with this? Now, I'm going to add these two equations together. These t's will cancel out. I'm left with m1 plus m2 times a is equal to m1 minus m2 times g. And I can solve for the acceleration finally and get m1 minus m2 over m1 plus m2 g. See what I mean? Now, again, this is a problem that plagues a lot of students because they don't really make those, they really don't orient their axes properly, or their tensions are different values, or so these forces have a lot of nuance that isn't really on the surface. All right. We can now move on to another type of example. Let's discuss friction now. This one's even trickier than tension or weight or normal force. So those are the three that we've become accustomed to at the moment. But let's bring this to example 7 then. What time is it, by the way? Ooh, nice, we're making good time. Really good time. All right, so I have a mass here. Okay? And I push it in this direction. So let's say that I push it for a certain amount of time. It's going to have a certain velocity at the end of that push, right? All right, and if I let it go, it will continue to move at that velocity forever. So if I push this desk, it's just going to keep going. Wait, that didn't work. All right, something is wrong here. There is something that's actually slowing it down. So its velocity was actually stopped. After I pushed it, there was no more force going in this direction. So we could have assumed that its velocity could have kept going. Another thing about static equilibrium is that if an object has a constant velocity, its net force will be 0. So it doesn't have to be stopped to be at static equilibrium. Get what I mean? So its velocity in this direction, as soon as I let go, started to slow down, which means there was an acceleration in this direction, right? Since there was no force on this, in this direction, and there was an acceleration in this direction, the only force acting on this desk had to be going in this direction. That's weird. So that means that there's some force that stops it. All right, I'm going to call this little f for the force of friction. Now, is it always there? Well, if I don't push this and I don't apply a force, and that force of friction is still going in this direction, then this chair would be pushed over there infinitely. That doesn't make any sense either. What's going on? Well, the friction force is very, very weird. It is what's known as a resistive force. Essentially,